Good day. My name is John Duhault, and I'm the Principal Geoscientist for Starboard Enterprise, a company based in Calgary, Canada. My paper today is called Microseismic Monitoring of a Tight Oil Reservoir, a Case History in the Cardium Halo Play. This paper provides an excellent example of how microseismic imaging can answer your hydraulic fracturing questions in a tight, unconventional reservoir. This e-lecture was originally published in Interpretation Magazine, Volume 6, Number 2 in May 2018, with my co-authors, Professors Dave Eaton and Per Kent Pedersen, both of the Department of Geosciences at the University of Calgary in Canada. The outline of the talk is basically going to be a hydraulic fracturing introduction. I'll go and show the geological setting for the Cardium Halo Play. I'll give an example of the basic seismic acquisition layout. I'll show you two projects, how the Cardium was recorded, and in the end I'll conclude with the value of microseismic. Why would somebody pay you to do and record microseismic? There are three types of hydraulic fracture geometries: hydraulic, propped, and effectively propped. And this will become important as we go through the slide deck. In the unconventional world, there is an issue of how close do you place your wells, but it's also not just the well spacing, it's also how close do you place your hydraulic fracture stages, how far your wells are apart, and if your reservoir is thick enough vertically, then how do you stack different layers of your subsequent wells. This map shown on this current slide shows the location map of the Cardium Reservoir in brown and the major cities in Western Canada, showing with Edmonton up in the northeast corner. And that Edmonton is about 160 kilometers to the Westpem project. The second project, also highlighted with the red star, is about 180 kilometers to the south, called Garrington. The image on the right shows the maximum stress direction as imaged from well bores that have been drilled in the Western Canadian Basin, and those are the black lines that run up through the direction. So in this part of Alberta, the maximum stress direction is north 45 degree east, more or less. Minimum stress direction is the lighter line that's running orthogonal to that. And this is important. Maximum stress direction is important because this is where the hydraulic fracture azimuth, or direction that the frac wings are going to go. This map here covers well over 100 miles from east to west and another 60 miles from north to south. The large black squares that you see outlining the map are about 10 kilometers by 10 kilometers. In Canada, they would be referred to as a township. You can see the halo wells are in red, and these are wells that were drilled after 2005. The main reservoir, the Pembina Reservoir, is actually the wells that are colored in green. And you can see there are literally thousands of wells. The pool was originally discovered in 1955 and is estimated to have over 7 billion barrels of oil in place, of which to date about just over 1 billion has been recovered. So that leaves a lot of room left to try to use horizontal wells to get the remaining hydrocarbons. The red wells, as you can see, flank the main green areas, and that's where a lot of the activity has occurred between 2005 and today. This stratigraphic chart shows where the Cardium sand sits in relative to two mudstones, the Blackstone below it and the Colorado or Lee Park shales above it. They are both late Cretaceous in age, and you can see that it is actually wedged between two shale beds. These shale beds do not produce hydrocarbons. There are no kerogen in these reservoirs. But the advantage of this is that when you produce the wells from the Cardium, there is no water production because it's quite wedged in between these two shales. The image on the left shows a small cross-section illustrating the pay zone from the halo zone on the left to the standard reservoir or the earlier Cardium reservoirs on the right. On the curve in each set of the wells drilled here shows that on the first curve is a gamma curve showing about 3 cycles of coursing upward geology. The other curves are the neutron density, and on the far right in both cases is the resistivity curve. What we show on this slide is that the net pay in the original Pembina reservoirs gets up to about 8.3 meters with an average porosity of 11%, using about a 6% cutoff. The halo wells, on the other hand, have a net pay of about 5.3 meters with an average porosity of 9.5%. What the reservoir looks like on an SEM is shown in the upper right-hand corner, where you can see the euhedral quartz structure, sand grains inside the sand reservoir. Now the trouble with this reservoir is also that it also has mixed clays, illite and smectite, and these will swell when encountered with water. And this was overcome using slickwater treatments. This next slide shows the layout that we would typically use to record microseismic. You can see a blue line on the plan view at the top showing the surface location down to the intermediate casing point, and it goes further to the south of the map to where you see the word total depth. If we jump to the side view, the lower image, you can see that the wellbore comes down and then starts to take a bend to the right, where you can see the word ICP. In Canada, this is where you'd set your first set of casing, and that bend from vertical to ICP is typically about 280 meters. Then you can see there's on the side view that we go through the Cardium reservoir out to a total length indicated on the map as TD, which would typically be about 1,400 meters. You can also see on that side view where we would like to record and put in our seismic monitoring shuttles or tools. Typically they would be 12 accelerometers, 3-component accelerometers, spaced between 10 and 20 meters apart, depending on how far apart we could record the data. You can also see now to the plan view that the monitor well is about 120 meters from the treatment well. This is important because in the Cardium imaging of the Cardium reservoir using microseismic, you need to be close enough to image the as many stages as you can. You'll also see on the map 3 vibroseis calibration points. This is important and necessary in order to calibrate the shuttles within the vertical section of the well so that we can accurately indicate where the shuttles are pointing so that we can actually accurately image the microseismic events. Now the first project I'm going to show you is from the Westpem area. You can see in the upper left-hand corner there is a star and a wellbore heading off to the northwest. And that would be treatment project 1, and I'll come back to treatment project 2 later. The larger squares that you see on this map are a square mile 1 by 1, or 1,600 meters. The black dots are oil wells, and some of the open dots with an arrow through them are injection wells. This is on the edge of the Pembina pool. Here's the picture of the microseismic recorded from this first microseismic project. You can see the horizontal wellbore travels from northwest down to southeast. You can see that we've imaged about 6 stages. You can see the monitor well is colored in red, and it's about 150, 200 meters from the treatment well. What you see on this is that also the well frac spacing is about 100 meters apart between each port. This is a gelled oil frac and creates what I call planar frac wings. And you can see that the microseismic events, say in the first stage, are all the blue dots head out in a very planar wedge, and it's very much confined to a single direction azimuth on the frac wing. The other thing to note on this is that the frac wings itself are asymmetric. They are not symmetric as per most of the microseismic modeling programs that are out in industry right now. This, we believe, is due to the fracture stress gradient that occurs in this reservoir. Now we're going to look at it in sectional view. Now in sectional view, you can see that the monitor well is the black line that runs really close to the blue events that are showing up on the sectional view. You can see that there are several dots that sit within the Cardium zone and Cardium sand, but you can see there's a lot of other events that occur above it. The key point here is these ones that occur above it, I would call those hydraulic events and not actually propped or effectively propped. Or another word that is used in the industry right now is that these would be dry events and not be connected to the main hydraulic fracture that we'd use to actually produce these wellbores. You can also see that the events slowly decrease in number and also start to spread out wider as you head further away from the monitor well. This is not because there are less events, it's just that we are further away and can't image all the events further out. And with modern processing, the events that you're seeing on this display would actually tighten up very nicely and be similar to what you see at the first stage. This shows the production from this Westpem well. It initially came on at about 300 barrels a day, and after the first year dropped to about 20 barrels a day. And as you can see from the graph, it's been doing between 10 and 20 barrels a day for the last 7 years. This actually, with minimal maintenance costs, is actually an economic well. Now I'm going to show you the second well in the Westpem area, treatment well number 2. It's a north-south well where we use 2 monitor wells. The key thing on these 2 monitor wells is they were drilled in 1962 and both produced about 130,000 barrels each. We took the production jewelry out of the wellbore and went in and did a well bond or a cement bond survey to make sure we had good bond on both wells in order to record the microseismic and be confident that we would get good data, which we did. This is the data that was recorded using those 2 monitor wells. You can see the 2 monitor wells are highlighted as the 2 vertical sticks on this sectional view, and you can see there are a lot of events that stay within the Cardium reservoir. However, you also can see there's a lot of events that we've highlighted as dry events that occur on some of the stages. This was typically occurring when the frac pressure went from 32 MPa up to 52 MPa. We do believe that they are dry events and just you're basically stressing the zone above it, but you don't have any fracture connection to them. And it did not prove to be a problem for these wells. This is the plan view of the 2. Key to note is that north is to the right of the screen, not up and down. And the monitor wells are highlighted with the green dots. You can see there's a gap in microseismic events between that do not go towards the wellbore, and that was done on purpose. We actually created a gap in the data so that we wouldn't frack into the existing wellbores. One concern is that the wellbores would bend into those existing wells because of pressure depletion. Well, it turned out that even the ones that are present and recorded did not bend into the old producers. Now, what's interesting is this is one of the few examples I've seen where the events on some of the frac wings are actually symmetric. Now, this may be due to the fact that in this immediate vicinity, the reservoir has dropped from a reservoir pressure of 21 MPa, that was the virgin pressure, down to 7 MPa. So, and that may result in the pressure, the stress gradient around this immediate area being a little more equal, so the wings are a little less asymmetric. But you can see on some, they're definitely asymmetric. This slide shows the magnitude versus distance plot. And what I'm trying to show here is this is basically if you're beyond 525 meters, you're not going to record much data in the Cardium zone. So you want to be closer, or as close as you can, if you're going to do downhole monitoring for the Cardium by getting in tighter within 100 to 200 meters, because you will not be able to image much above 500. Now, what I'm also showing here is that the magnitude of events that are recorded in this area are between -2 and -3. So the highest magnitude event that we recorded here is slightly above -2. And a lot of them we would record at -3, and once you get below that, it's pretty low amplitude. What I'm showing here, why the Coke can is there, is that a -3 event is actually equivalent to a can of Coke falling off a table. Say a 1 meter high table, you drop the can of Coke, that's how little energy is being recorded here. And the -2 is actually if you took a 4-liter jug of milk and pushed that off the table and it fell on the ground. I mean, I could use a 4-liter jug of beer, but why would I waste beer? And we would use milk. So is not a lot of energy being released on these. And so getting good images, we are not, when we record hydraulic fractures, we are not getting back a lot of the energy. A lot of the energy actually appears to be lost to heat and friction when the wellbore is actually stimulated. This next slide shows the anisotropic moment tensor inversion. It's produced by Scott Leaney and came out in 2014 at the CSEG recorder. You can see on the right is the plan view, and you can see the events. The image that he's using shows a direction north 45 east. What Scott has done is instead of using beach balls to indicate how the moment tensor has occurred, he's actually using hockey pucks. Scott being a Canadian, hockey's easy. So the thickness of the discs that you see are actually the part of the energy that's involved, and if it was a tensile event, it would be a very thick hockey puck. The key piece I find is that you can actually get a sense of whether it's dip slip or strike slip from the processor, the imaging that he has provided in his paper. You can also see on this one that the dry events that are higher up in the section are at a different azimuth and help to support the idea that these are not connected to the hydraulic fracture treatment below it. One key piece of this is that is production. So you can see on this graph that over 5 years, the well we were looking at, well number 2, has produced just over 70,000 barrels. And to indicate that this is is not a one-off. I've also shown two other wells drilled to the west of that same wellbore that will produce greater than 70 to 80,000 barrels. This indicates that even though the reservoir pressure has depleted down to 7 MPa, there's still opportunity for recovering significant hydrocarbons. These wells will be economic. I'm now going to show you the Garrington projects, and this current slide shows the location map of the Garrington project located at the very bottom end of the slide. It again is about 160 kilometers south of the city of Edmonton. The brown show the shore face sands that the Cardium Reservoir has been produced from. And we're going to move forward from there. The Cardium treatment wells were two wells that were drilled 6 months apart. Well 3 was drilled as a Slickwater, and well 4 was a gelled oil. You can see from this map they're both in length of about 1,400 meters. This is a geological cross-section, shows two wells in the immediate area. The well on the right shows the closest vertical well to the two horizontal wells. The curves are gamma on the left, followed by a neutron density and density curves, then followed by a SP and then resistivity on the right. You can see that there's a nice coursing upward sequence on the gamma on the well on the right, and it's capped by about a meter thick conglomerate, which adds significant production to that well that actually produced about 90,000 barrels in its lifetime. The well on the left also shows a nice coursing upward sequence in the gamma ray sequence, has excellent resistivity, and also has a little bit of conglomerate cap. The reason why I'm showing this well is this is the well that we actually used to monitor the two wells that we're about to look at when we see the microseismic. This is the layout that, using that same wellbore, you can see that the geophones were placed above and below the Cardium zone. And you can see the VP, VS, and density curves that were used in calibrating the velocity model for the microseismic. This slide here shows the slickwater versus foam water frac treatments in the Garrington area. The image on the bottom shows the slickwater stages, and you can see from the horizontal grid, these are about 200 meters apart, or the whole wellbore length is about 1,400 meters. In the slickwater, you can see a number of the microseismic events actually start to cloud together. Individually, they show as a dendritic or shattered glass look. This shows that we've effectively stimulated the reservoir throughout the Cardium zone using this methodology. When we go to the foamed water version, you can see that there are planar frac wings. You can actually see a line or a break between each of the frac stages. This implies that we are not stimulating the reservoir between those two stages, and not the best thing on a go-forward basis. One of the other key points in this area is that you can see where the monitor well is relative to the two well bores. Now on the monitor well, when it records the slickwater, you can see that all the vents are closer to the monitor well. The comment has been is that the asymmetry of the microseismic events has been due to the monitor well location. But you can see that on the well 4, the maximum vents are actually away from the wellbore, again in the northeast direction. And in the southern well, the slickwater, they're actually also in the northeast direction, but heading towards the monitor well. This implies that we have a stress gradient in the area. Now we're going to look at sectional view. The view on the left is the slickwater, and you can see that the slickwater actually keeps the microseismic vents within the Cardium zone fairly well. When you look to the right on the gel foam, you can see there are a lot of vents that go above and beyond the zone of interest. It's only about 40 to 50 meters, but that's a lot of events and a lot of energy that's gone up and below the actual Cardium sand, and it's not a good use of frac energy. This is a schematic view showing the two treatments. Well, the slickwater is on the left, and shows again that it's fairly well confined to the reservoir. The gelled foam, you can see, has a fair bit of height growth to it, a fair bit being about 30 to 50 meters, and probably has a lot of dry or unpropped events. Taking the data that we started with, the University of Calgary went and did some match filtering analysis and was able to find more and more events by using what David Eaton refers to as a parent and child events. In the first, at the upper slide, going from ABC, you can see that there was two stages he used, and when the first analysis gave us about 195 events. When David and his team worked on it, they got about 600 events, or about 4 times more. And then the last slide in C shows the interpretation of possibly induced natural fractures that are picked up. This allows us to see a lot more events and can show that we're actually stimulating a fair bit of reservoir that wasn't as clear on the first analysis. The images on D, E, and F are two different stages, but also show the same general character. 4 times more events, and again, a reactivation of natural fracturing, but also more events that shows we're doing an effective job of stimulating the Cardium reservoir. Now we look at the two. This is the most important thing when it comes to how are you fracturing your well. Well 3, the Slickwater, has produced about 60,000 barrels in a 5-year timeline. Well 4, the gelled water or foamed water well, has only produced about 30,000 barrels, showing you that is half the production. So choosing your proper treatment technique is important. Well 4 is not economic. Well 3 is. What I've also illustrated is 4 other wells from just to the west of the 2 wells that we shown earlier, showing that it wasn't just a one-off. There are several wells. There's even one that's going to produce even more oil than the well 3. Again, these would be economic at this point in time. Now we're going to roll into the conclusions. Why do you want to get microseismic images? 1, you can get hydraulic fracture length. That will determine how far your wings are going out. Now when you analyze it between whether they're hydraulic events, propped events, or effectively propped events, that'll start to determine how you tighten up your stimulated reservoir volume. Next, hydraulic fracture height. You want to be able to stay within your zone as much as you can when you fracture your reservoir. The more you stay in zone, the more effective your frac is going to be and the better production you're going to get. Hydraulic fracture azimuth. Which way is it going? Is it following the maximum stress direction? Now, if you lay it out so you can maximize your production by taking that into account, and also indicating other existing well bores so you don't encounter them and can maximize your reservoir's production. Fracture treatment style. We've shown from the last example at Garrington that has a significant impact on how you're going to be able to produce your reservoir. If you haven't done any microseismic on any of the reservoirs you're pursuing, this is the point in time where to recommend to your engineer or senior management that in order to understand what your fracture treatment is doing is to do microseismic to understand the fracture treatment and provide a better completion process. And lastly, by understanding the moment tensor inversion of the actual events, you can be able to tweak your fracture treatment program in order to provide a better response if the well or events are dip slip, strike slip, or even tensile, and be able to understand, aha, this is how this works, and we may be able to improve our fracture treatment model. And in conclusion, where is the value in using microseismic? Well, it really comes down to helping your projects move forward and how completion geophysics can increase the value of your property. Biggest one is determining stimulated reservoir volume. By understanding how far your frac ports and how much reservoir is stimulated by those frac ports, you can start to see that you can either tighten it up or maybe you are too close and you can spread it out. Also, on the next step, by identifying and by working with moment tensor work, you can identify what type of fracture is occurring, and you may be able to modify your fracture treatment style to enhance that fracture slip type. Additionally, by seeing what the stress gradient is, if you have asymmetric fracs, that may allow you to place your wells differently in order to maximize the production from your property. Also, by seeing the microseismic, you may be able to see different responses and identify natural fractures. Sometimes natural fractures are your friends, sometimes they're your foes, depending on the environment you're in. This becomes important on where you place your next wells and how you stimulate them. And lastly, you put all these together, it can help you by looking at the microseismic events and your engineers to look at it to go, wow, we could modify our treatment style and get better production. By imaging with microseismic, you'll be able to do that. Thank you for your time.